Hey everyone, my name is Carson Culler, and this is my final parallel program for Computer Science 551, which is numerical and parallel programming at California State University, Chico. So the fun thing about this program is that it really allowed us to explore a topic of our interest. We could either kind of base it off of a previous assignment that intrigued us or go in a totally new direction. The fun thing about the assignment is it kind of forced us to learn a few things. First of all, we had to learn a computational algorithm that was going to be used, and we also had to use some mathematical concept, theory, or proof to kind of back our findings. After finding both of those, we had to put them together to make a sequential program, and then with that sequential program, we then had to use a parallel programming method to then parallelize it and get speed up. So I opted to go with prime number searching and large semi-prime factorization. This stemmed from a previous assignment we had in the semester where the assignment was just that. We had to find the largest prime numbers under 1 billion and then calculate the semi-prime that is constituted of those two prime numbers. To do this, using the computational algorithm that was used is the sieve of Eratosthenes. It's a very common algorithm for this case. It essentially crosses off numbers on a list of all the numbers based on factors of known non-primes. For example, we start with 2, which is a prime number, but any multiple of 2 is not a prime number. So we can just start multiplying 2 over and over and over again, cross those all off. Do the same thing for 3, 5, 7. Take all the known primes, any multiple of those is not a prime. By the time you get to n, you have found all of the primes. Any number that has not been crossed off is a prime number. It's a fairly straightforward algorithm. It's fairly time efficient, and it's widely known. So that once more, that's the sieve of Eratosthenes. I then backed this program with the prime number theorem, which is a mathematical theorem that basically states n over log n is approximately how many prime numbers are less than n. It's never accurate. It's an approximation. It's not 100% true, but I will show throughout this demonstration that as n grows, that approximation gets closer to 100%. Okay, so why is this relevant? Why is this prime number searching and semi-prime calculation, why is this relevant in the real world? Well, from all the research I've done, I have found that large prime number searching and semi-prime computation is a very necessary step in encryption. For example, using RSA keys, to generate an RSA key, you need to first find a very large prime number. I can't tell you exactly why that's necessary, I just know that it's an important step in the process. And then as far as matching keys, you need to generate semi-primes using 2 prime numbers. And so while this does not by any means achieve that, this program that I'm going to show you is a very necessary step in that process. So if you're interested in encryption, RSA keys, things like that, this is a pretty sweet algorithm. And then as far as why I chose to do this, well, thinking back to that assignment I mentioned where this was the assignment, I really enjoyed the idea. You know, the overall idea of a sieve doesn't really seem that hard, and so I tried to make my own from scratch. While it did work, I was not able to get it parallel. It was frustrating. I tried, couldn't get it to speed up. So at the last minute on that assignment, I jumped ship, I abandoned my code, and I ended up using a starter code that was provided by Professor Siewert. I was able to get speed up on that, turn that in, whatever, moved on. I wanted to revisit my code because I enjoyed it and it makes sense to me. And I wanted to see if I could get the sieve to speed up. Spoiler alert, I didn't. I failed again. I tried, could not get it to speed up. Something about the way I implemented it, it just is really difficult to speed up, and I wasn't able to make it happen. That being said, my program does satisfy the requirement of the project because I did add a feature. That was an option. You could take a previous assignment, add a meaningful feature. For example, mine, after it finds the semi-primes under n, it then prompts the user to enter 2 values. Let's say the user enters 300 and a second number being 50,000. The program then does a brute force search and then returns what the 300th prime is, starting at 0, and the 50,000th prime. It tells you what placement primes those are. Like I just said, this is done using a brute force search, and that I was able to make parallel and get pretty good speed up on. So that's what we'll be focusing on for the majority of this presentation. But that being said, I'm going to walk through the code line by line. I'm just going to quickly explain how it all works and how it's all related to each other. And then after I go over all the code, I'm going to show some example runs and how it works. And then finally, I'm going to compare the speedups to Amdahl's law and see overall how well this code runs in parallel. So let's get right into it. Okay, so starting off with the code, I just want to quickly go over the make file. When I compile, I'm compiling with -f openmp. I forgot to mention in the intro, my parallel method that I ended up going with was openmp. I include -f openmp in the compiler to make that shared memory happen. I also include -lm because at one point I used the math library. And then lastly, I compile with -03 compiler efficiency. I truthfully didn't really notice much of a difference between -02 and 03 in here in the runs. So I just left 03, might as well just make it efficient, quick, why not? Alright, so taking a look at the code itself, it is about 200 lines long, so I'm just going to quickly go through it. We include all our necessary libraries, the main two being openmp and time. We definitely need those libraries. I'm defining my array of numbers to be 1 billion characters long, and then I'll come back to this program. But starting off with main, to use, we kind of call the function. We implement we input n. This is going to be how big our array is initialized to, and then the number of threads that we want to do. I always enjoy passing in the thread count by command line because it allows you to test sequentially and in parallel without having to recompile in between. I just like that because it makes it kind of a fair comparison. Sometimes it's not fair if you run it, recompile, run it again. This way I don't need to recompile. Alright, that's what I'm doing right here. I'm just setting n to be a command line argument. I'm setting the number of threads to be a command line argument. And then down here, I am initializing the array. So we have an array, let's say n is 1,000. We're going to initialize the first 1,000 elements as 1. This little section I was able to get to run in parallel. To do this, I just made a chunk size variable, just splits n based on the number of threads there are, and then just a simple pragma line that schedules each chunk size its own section of the array. They all populated as 1. Now the array's full. Right here, this was a more in-depth version of this. They essentially do the same thing. I was obtaining my current thread count. I was kind of setting the chunk size manually. I was then setting the start and end for a given iteration, and then I was just setting those to 1. I then found out later that this does that for me. This openmp schedule directive already does that. So I was able to use this. Alright, so once our array is full, we're ready to get going. I should have mentioned I was timing that just to see how much time we shave here. We'll go over that more later. Anyways, once that is done, we print out how long it took to initialize the array. Again, not as important as the rest, but important nonetheless. Right here, we are setting 0 and 1 to be not prime because they're not. When we get down here into the algorithm, due to the nature of how the algorithm works, we want to start iterating from 2. 2 is the first prime number, so that's where we want to start. So we just have to manually set 0 and 1 to be not prime. The rest is done for us, luckily. Alright, and so then time to start the actual sieve. So to do that, we're going to start the clock, and here we go. We start at 2. Now from here, you would think that we would iterate through n, but no, we're actually going to iterate through the square root of n. That is because once we make it to the square root, from the square root to n, the multiples have already covered that for us. It would just be a waste of time to iterate through that because we wouldn't be doing anything. We would just be iterating for no reason. So we're going to iterate through the square root of n, and if it is found that that current number is prime, we are then going to call that on our prime function. So let's go ahead and take a look at that. We're going to pass in that number, that prime number that we just found, and the overall n. So going up to this function, what happens then? Well, we are going to start with the square of that number. So let's say we pass in 2. It's the first number, 2 gets passed into the function. Well, this for loop is going to start at 4. 2 is a prime number. We don't want to check that off. We're going to start at 4. And then all the way up to n, every multiple of 2 is going to get crossed off. So we're going to cross off 4, 6, 8, 10, 12. Literally all the even numbers gone immediately. Beautiful. Another run, 3 will get passed in. That'll get 3, 6, 9, or it'll start at 9. So it'll get 9, 12, 15, 18, 21, all those. You can see how this, over time, will start crossing off all of these numbers. You can see a few failed attempts that I had at making this parallel. I tried a few different things. Nothing was seeming to work. I would either get the right answer and a lot of slowdown, or I would get the same speed but the wrong answer. It was a big pain trying to make that work. Here is another instance where I tried to manually make this for loop parallel. Didn't quite work out for me, but I tried to just divide the work manually, split up the main array into chunks. Unfortunately, I just couldn't get it to go parallel for me. But it's okay, because you'll see that I did get speed up elsewhere in the program. So once we're done with that, once this for loop ends, we're done with the sieve. The sieve is finished. So we're going to end the clock. And then now, this was kind of the portion of the assignment where we had to find the 2 largest primes and then the semi-prime that is made up of those. So to do that, we're just going to start at the end of the list and iterate backwards. When we find a prime number, we're going to push it into this 2-element array of primes. Once we get both of our primes are found, we're going to break out of this loop. We have our 2 highest primes. Then to print how many primes there are in total, we're just going to sequentially iterate all the way through n, and we're just going to add them all up. That'll get printed. Yes, this can take a little bit of time, but this portion isn't timed anyways, so it's not going to affect our run times either way. Moving forward, we can, right here, we are making the semi-prime using those 2 prime numbers that we just found. And then right here is where we're going to be doing the prime number theorem. I'll talk about that more later when we actually see it in action. Alright, and then once all that's found, we're ready to print. We print how many primes there are in total. We're going to print how many primes according to the prime number theorem. We're going to print the largest semi-prime, which is, again, from our 2 primes that we found. And then lastly, we're just going to print how long it took to perform the sieve in total. So that alone was the end of the assignment earlier in the semester. But now here's what I added for the final project. Next up, we are going to input 2 numbers from the user. So we're going to ask the user to give us 2 numbers. Let's say, again, the user gives us, 10 and 50. We are going to make sure that both of those are within bounds. We can't ask for the 1,001st prime if we only found 1,000 primes in the first place. It's got to be within limitations. So as long as both entries are valid, it's time to find what those primes actually are. And again, we're doing this using a brute force search method, which is just iterate through everything and check everything no matter what. Alright, so getting right on into that, we are starting the clock. We are setting just some variables to get ready for us. And then here we go. Iterating from 0 to n, if we found a prime number, we are going to increment the count. Next up, we're just checking if the current count equals either of the numbers input by the user. If it does equal those inputs, we're going to set them accordingly. This logic can get a little weird. If it equals either one of them, If first hasn't been set yet, then we know this is the first prime number that we found from the user. But if first is already populated, then we know that this has already happened once. So we're going to populate the second one. We're going to populate the second one. This would be a good spot for a break right here to get out of here and save some time. However, this is what I ended up making parallel, this entire for loop. So, you can't break out of that, or else your pragma won't work. As far as the pragma itself, I'm using the given number of threads from the user, and I'm constituting count2 first and second as shared, so that way all threads can access them equally. You can see in here where, along the way, I tried to use some OMP criticals to completely make this thread safe. However, when I would do that, I would get a lot of slowdown. Obviously, as it makes this a critical section, it's going to go slower. But in my experience, at least with my compiler and everything, I got the same answers without the criticals. So I took them out, and I do get speed up now, and I still get the right answers. So as far as the OMP criticals go, I'm not concerned with having them commented out. I just wanted to leave them in so I could talk about this. All right, so moving forward, once that is done, we're going to stop the clock, and we're pretty much done with the code here. We're going to stop the clock, we're going to calculate our new semi-prime. This part, completely unnecessary. It just makes sure that when it's printing, the numbers have the correct suffix. It was a little extra something that I wanted to do. And then as far as the final prints go, we are going to print what the primes are that you asked for. We're going to print the semi-prime that is made up of those, and then we're going to print the time that it took to do that search. Right on, so that is all of the code explained, and with that being said, let's take a look at a few runs. So first off, I want to demonstrate just a make clean and a make to show that it does compile with no warnings, and the dash wall flag is enabled. So clean code, yay. And as far as running it, remember we call the executable. We can call a size of n. Let's do 1,000,000 for now. And then a thread count. We'll go sequential for now. So you can see that it initialized the array pretty fast. It performed the sieve. And then it's going to ask for 2 prime number placements to compute a semi-prime. So it found 78,000 total. So let's ask for prime number, I don't know, let's try prime number 312 and 50,000. Why not? And it did it for us. It found the 312th prime and the 50,000th prime right there. It's going to tell us what their semi-prime is and how long it took. As far as verification goes, I kind of just Googled these to make sure they were the same. So I could quickly Google what is the 312th prime. 2069. Boom, that looks good to me. And let's go 50,000th. What is the 50,000th prime? 611,953. Cool, so it looks like it worked pretty good for us. And right on. So we can also see how this scales up to 1,000,000. Or I should say 1,000,000,000. So let's try a few different numbers this time. So we'll go 1,000,000,000 as the size of n, and we'll stay sequential on this one. But then I want to show the speed up. So you can see it took a little bit longer that time to initialize the array, and it takes about 9-10 seconds to do this. Yep, so a little under 11 seconds to complete the sieve. I want to do a little bit different numbers. Let's stick with 50,000. Yeah, let's stick with 50,000. And then let's try 1,000,000. Why not? All right, so we got 50,000 and 1,000,000. All right, so we did that sequentially. We have a bunch of times. We already know that 50,000th works. Let's check what the 1,000,000th is. What is the 1,000,000th prime number? 15,485,863. Right on. So it works right on. We have some times, and we have the right answer. So let's see how this scales. Well, let's start adding threads. You can see right off the bat, it populated the array much quicker. It's going to perform the sieve in about the same amount of time. That's because that part's not parallel, like I was saying earlier. And let's do the same numbers, 50,000 and 1,000,000. Right on, so we got the same numbers, and it went in about half of the time. Right on. One thing I do want to circle back, I apologize, I forgot to mention this, the prime number theorem. I just want to touch on this real quick, I meant to earlier. The prime number theorem was the mathematical proof that I wanted to use just in conjunction to this program. The idea of the prime number theorem is that n over log n is roughly how many prime numbers there are from 0 to n, but the larger n gets, the closer that approximation gets. So right here on my calculator, if I check this percentage, if I go 72,382 divided by 78498, how many primes there are and how many the PNT found, I get about 92%. So the PNT was about 92% accurate. Over here, we have a much larger n. So if I go 48254,942, how many primes the PNT thinks there are, divided by 50,475,000, or 847,534, I get about 95%. So you can see how as n goes up, our PNT is a little more accurate. So that was kind of the research I did into the mathematical proof. All right, going back to what I was talking about, we can see with one thread, it took about 2/3 of a second to initialize the array. With two, it took about 0.4 seconds. Sequentially, it took about a second to complete the brute force search, and with two, it took half a second. So let's just keep scaling this. Let's try 4 threads. I'll keep the numbers the same. You can see even quicker to initialize the array. And then this will finish up, and I will put in the numbers, 50,000 and 1,000,000. Still get the same numbers, and even faster. Okay, lastly, I will just show it with 8 threads. So you can actually see that right here, we actually have a little bit of slowdown initializing the array. I will say that is definitely an outlier. I'm only showing the times once right now, just for time's sake. But in the write-up that I'm about to show you, I took the times 10 times each and then took an average. Okay, I'll put in the numbers. And we will see it went even quicker with 8 threads. So we can see that it's scaling very well. But how well compared to linearly? Well, let's take a look at the findings I had. Like I said, all of these findings, I would take the time, I'd run the test 10 times, and then I would average those times and put them in this table. So let's see how well it really scales. So I checked with n of 1,000, n of 1,000,000, and n of 1,000,000,000. Let me check my time, okay, and n of 1,000,000,000. Well, looking at this, as far as our primes under 1,000 go, sequential it went pretty quick, and we actually got a slowdown here. And I think that this makes sense because n of 1,000, that's so small that there really isn't that much work to be done. The actual overhead of setting up the different threads takes longer than if you would have just done it sequentially with one thread. So 1,000, we get massive slowdown. 8 threads. I will change that for the submission. These should say threads, not cores. We get about an 18 times slowdown on 1,000. I'll just change this one so it makes sense. Cores would have been if I was using MPI. My apologies on that. However, we can see that it does scale well. On 1,000,000, we get up to almost a 4x speed up on 8 threads. And then on 1,000,000,000, we get almost a 5.5 times speed up on 8 threads. So this really does make sense. As there's more work to be done, you benefit more from a divide and conquer workload. It's not very useful on n equals 1,000 where there's not a lot of work to do. But when n is 1,000,000,000 and there is a lot of work to do, splitting that work up makes sense, and it definitely gets a lot of speed up. So to calculate Amdahl's law with that, or to analyze Amdahl's law, I wanted to take a look at how much of this portion, just the brute force portion, is actually running in parallel. So to do that, I just grabbed my best speed up. So my best speed up was 5.35x. To obtain that speed up, I had 8 threads. And then plugging it into this P equation, we see that P is 0.929. This means that as far as that brute force section goes, about 93% of it is running in parallel, and about 7% of it is running in sequential. So that is pretty solid. That's a very good P score. Ideal is 100%, but that's virtually impossible. That being said, I do want to compare my speedups to ideal linear speedup. Ideal speedup is assuming that you have 100% P instead of the 93 that I have. So looking at when n was 1,000, obviously this graph is skewed. We got slowdown compared to the yellow ideal speedup. Looking at 1,000,000, we got pretty good speed up. You can see that around 4 threads to 8, we start to differ from that ideal. But then when we look at 1,000,000,000, we can see that we actually stuck pretty close to ideal speed up. We're following the same trend, at least it's more accurate than its two counterparts were. I think that had we pushed on, maybe gone to 1,000,000,000,000, maybe even beyond that, had I had a supercomputer, I think we would have seen trends going closer and closer to ideal speed up. So I would say that this program scales very well. Now, one last thing that I do want to quickly go over, I'll get this out of the way. While I only just analyze speed up of one portion, I only just analyze speed up of my brute force when that wasn't even the longest part of the algorithm. The longest part was the sieve itself, which was running sequentially every time. So I do want to kind of just use the Unix time command to basically see how much time did I actually shave off of the whole program. So to make this as accurate as possible, I'm going to take out the user input, and I'm just going to hard code it. This way we don't have to break for user input. The code can just run as quickly as possible. So I'll put in those values that we were just using. I will recompile. And now I want to go time. Like I said, I'm going to use the Unix time command to analyze this. We're going to go 1,000,000,000, and we're going to start sequentially. One thing that I did forget to mention earlier, it is in my write-up, but I forgot to mention, I'm running all my testing locally. This is not on ECC Linux. This is all local on my machine. I apologize for not saying that earlier in the video, but it will be in the write-up. So we'll see that sequentially took a little under 14 seconds. Let's try 4 threads. And then I'll just try it with 8 at the very end, and we'll just see how it goes. Actually got some slowdown. Interesting. What about 8? Maybe that was just an outlier. If 8 gets speed up, I'll go check that out again. Like I said, every now and then there are some outliers. That is why when I was recording the times, I would run it about 10 times and take the average. Yeah, see, we can see it went faster with 8. So I just think that middle one was just an outlier. I'll run it one more time just to be safe. It's always tricky, just doing one run and trusting it blindly. And there we'll see. Yeah, so it's slower than the last one. So I would just trust the times, running these over and over and over again, taking the averages. It's kind of hard to deny the speed up. And it's tricky considering the portion that I parallelized is pretty insignificant compared to the entire lab. For example, sequential, we just got a 13.884. Again, This would be much more accurate had I ran this many times. Divided by 13.751. So we got a 1.01x speed up based off those two runs alone. I'm sure if we ran it a few more times, we would see a better speed up, but really, in the grand scheme of things, not great speed up. However, I do think that I still accomplished the point of this assignment in speeding up my brute force algorithm. Okay, I will wrap this up quickly because I'm going pretty long. I apologize for the long video. I was kind of rambling, getting away from myself. I kind of just want to close by saying this was a pretty fun project. I really enjoyed learning more about these things, and while I couldn't get amazing speed up on the overall project, I think that the speed up I got alone on the brute force and the array population, it kind of demonstrates good use of OpenMP. I believe that I tackled the triple threat of the class. I think I learned a lot about parallel programming. I know I didn't use MPI on this program, but I did learn a lot about MPI. But I learned a lot about what to do and what not to do with OpenMP. I enjoyed learning about the sieve of Eratosthenes algorithm, so that kind of tackles the programming algorithmic idea. And then, while I didn't talk about it much in the video, I did learn about the prime number theorem with math. I never knew that you could take n over log n, and that's about how many primes there are under. I think that's a pretty, cool thing to know. And yeah, with all that being said and everything done, I enjoyed this project, and I hope you enjoyed my work and my performance on it. Thank you very much for watching, and I will see you next time. Bye.